Hi, in this demo we're going to show you how you can train a model using Amazon SageMaker. I'm already in my Jupyter notebook. I've loaded some data and done some pre-processing. So let's have a look. I'm using the wine dataset, which is available from the UCI repository. I have about 1600 rows and 12 columns. The first column is quality, which is a numeric, and we have a bunch of other columns which are to do with wine. If I take a look at the quality column itself, you can see we have 6 unique values, and this is going to be the target column that we're going to try and predict. We have to split the data into a test, train, and validate set. To do this, we're going to use the train test split function from sklearn. This is going to take our data frame and it's going to create a test size of 0.2 or 20%. That should leave us with a data frame with 80% of the data and another data frame with 20% of the data. We're going to specify that we stratify the quality column. And what this is going to do is make sure that our quality is split between the different data sets. If we don't do this, we're at risk of maybe getting a data set that has all 10 of the 0 values in. And that might be missing then from the training set or the test set. We're then going to take the test and validate data frame and we're going to split that in half. And that gives us the test and the validate data frames. If we take a look at the shape of those, you should see we're about 80% in the training and we're equal between the test and the validate. If we take a look at the value counts, again you can see that we're pretty much split between the two 10% sets with pretty much equal values, and then we have our 80% training set there. The next thing we want to do is upload the data set to S3. To do this, we're going to use a function of the data frame called toCSV. And what this is going to do is take our data frame and convert it to a CSV file. We're going to specify no header, which means we won't get the column names. And then we're going to just upload it to S3. So let's go ahead and do that for the 3 data sets. Next up, we need to create the estimator. For the estimator, we're going to grab the container image for XGBoost. We're then going to set some hyperparameters. The most interesting one at this stage being the number of classes being equal to 6. And that's how many different values we have for our quality column. We're then going to specify that we use 1 instance of an M5 extra large to train. The final thing we need to do is wire up the data. So we're going to create 2 input channels. We're going to create a train channel, which points to the training data, and a validate channel, which will point to the validate data. Once we've done that, we're going to train the model with the data. This is going to take a few minutes to complete, so while that's happening, let's go take a look at the console. Here we are now in the Amazon SageMaker console. If I refresh the screen, you can see we've now got a job in progress. And if I click on this, I can see all of the data that we've set up previously. We've got our image type here, we've got our input training data, we've got our validation data, and so on. I could have created the training job within the console, but since we typically create multiple training jobs, it's good practice to learn how to code this. Let's flip back to the notebook and let's just wait until this is done. It should take a couple minutes, so we'll pop back then. So here we are, our training job's complete. And what we can do is go view some metrics from the training job. You can see we've got M error, which is the number of wrong cases divided by all of the cases. And we've got that for both the training set and the validation set. Now we'd expect the training set to be pretty low, but you can see our validation set's around 30%. For M error, the lower the better. We can test our model against the test set, which the model's never seen, and that will give us some more information about how well the model's performing. So let's go load that test set into S3, but this time without the target column. Then what we're going to do is perform a batch transformation on the test data. Now we could host the model and run inference against each line of the test data, but a more efficient way of doing this is to actually use the batch transformer. What it's going to do is spin up an instance. In this case, we're going to use one instance, an M5 extra large. It's going to run our entire test set through that and generate the results. And then it's going to shut the instance down. And this is a great way to automate some testing. So let's go ahead and run that. Again, it's going to take a few minutes just to load the instance, run the inference, and then shut down. And we'll pop back when that's done. Okay, our batch transform's complete, and the results will be in S3. So let's download them. We've downloaded them into a data frame which we've named target predicted. Since we have the original data set with the actual target value, we can go extract that and call that test labels. With both the target predicted and the original predicted value, we can go create a confusion matrix, which will give us an indication of how well the model's performing against each of the quality values. If that's not clear enough, we could also create a confusion matrix heat map, which will show us all of the model in a nice chart. Of course, we're not finished here. We'd want to go tune the model, tune the hyperparameters, do some more feature engineering, and repeat the process until we found a model that performed well for our business needs. That's it for this demo. We'll see you in the next one.
Hi, and welcome back. This is section 6, and we're going to look at hosting and using the model. In this section, we'll look at how you can deploy your trained model so it can be consumed by applications. After you've trained, tuned, and tested your model, you'll learn more about testing in the next section, you're now ready to deploy your model. If you're thinking that we're looking at the phases out of order, here's why we're discussing deployment now. If you want to test your model and get performance metrics from it, you first need to make an inference or prediction from the model. And this typically requires deployment. Deployment for testing is different from production, although the mechanics are the same. Amazon SageMaker provides everything you need to host your model for simple testing and evaluation, from a few requests to deployments handling tens of thousands of requests. There are two ways you can deploy your model. For single predictions, you can deploy your model with Amazon SageMaker hosting services. SageMaker will deploy multiple compute instances which run your model behind a load-balanced endpoint. Applications can call the API at the endpoint to make predictions. With this model, you can scale the number of instances up or down based on demand. To get predictions for an entire dataset, use Amazon SageMaker Batch Transform. Instead of deploying and maintaining a permanent endpoint, SageMaker will spin up your model and perform the predictions for the entire dataset you provide. It will then store the results in Amazon S3 before it shuts down and terminates the compute instances. It's useful for performing batch predictions when you test the model. You can quickly run your entire validation set against the model without writing any code to process and collate the individual results. The goal of the deployment phase is to provide a managed environment to host models for providing inference securely and with low latency. After your model is deployed into production, you should monitor your production data and retrain your model if necessary. Newly deployed models need to reflect the current production data. New data is accumulated over time, and it could potentially identify alternative or new outcomes. And so deploying a model is not a one-time exercise. Instead, it's a continuous process. With one click, you can deploy your model on Amazon ML instances that can automatically scale across multiple availability zones for higher redundancy. Just specify the type of instance and the maximum and minimum number of instances desired. SageMaker will take care of the rest. It will launch the instances, deploy your model, and set up the secure HTTPS endpoint for your application. Your application only needs to include an API call to this endpoint to achieve inference with low latency and high throughput. With this architecture, you can integrate your new models into your application in minutes because changes to the model no longer need changes to the application code. SageMaker manages your production compute infrastructure on your behalf. it can perform health checks, apply security patches, and conduct other routine maintenance, all with built-in Amazon CloudWatch monitoring and logging. After you've trained the model, you can create the endpoint either in code or by using the SageMaker console. If you're planning to host only a single model, you can create an endpoint for that model. But if you're planning to host multiple models, you need to create a multi-model endpoint. Multi-model endpoints provide a scalable and cost-effective solution for deploying large numbers of models. They use a shared serving container that's enabled to host multiple models. This reduces hosting costs by improving endpoint utilization compared to using single model endpoints. It also reduces deployment overhead because SageMaker manages loading models in memory and scaling the models based on the traffic patterns to them. When you deploy machine learning models into production to make predictions on new data, you need to make sure you apply the same data processing steps that were used in training to each inference request. Otherwise, you can get incorrect prediction results. By using inference pipelines, you can reuse the data processing steps from model training during inference without maintaining two separate copies of the same code. This helps ensure the accuracy of your predictions and reduces development overhead. Because SageMaker is a managed service, inference pipelines are completely managed. When you deploy the pipeline model, the service installs and runs the sequence of containers on each EC2 instance in the endpoint or each batch transform job. Additionally, the sequence of feature processing and inference runs with low latency because the containers are collated on the same EC2 instances. Some key takeaways from this section of the module include these points. You can deploy your trained model by using SageMaker to handle API calls from applications or to perform predictions using a batch transformation. The goal of your model is to generate predictions to answer the business problem. Be sure that your model can generate good results before you deploy to production. Finally, use multi-model endpoint support to save resources when you have multiple models to deploy. That's it for this section. We'll see you in the next video. Hi, welcome back to Module 3. In this section, we'll look at how you can evaluate your model's success in predicting results. At this point, you've trained your models. It's now time to evaluate that model to determine if it will do a good job predicting the target on new and future data. Because future instances have unknown target values, you need to assess how the model will perform on data where you already know the target answer. You'll then use this assessment as a proxy for performance on future data. This is the reason why you hold out a sample of your data for evaluating or testing. An important part of this phase involves choosing the most appropriate metric for your business situation. Think back to the earlier section on problem formulation. During that phase, you define your business problem and outcome, and then you craft a business metric to evaluate success. The model metric you choose at this phase should be linked to that business metric as much as possible. There's often a high correlation between the two metrics. In addition to considering your business problem and success metric, the type of ML problem you're working with will influence the model metric you choose. Throughout the rest of this module, we'll look at examples of common metrics used in classification problems. We'll also look at common metrics used in regression problems. We're going to start by considering a simple binary classification problem. Here's a specific example. Imagine that you have a simple image recognition model that's labeling data as either cat or not cat. After the model's been trained, you can use the test data set you held back to perform predictions. To help examine the performance of the model, you can compare the predicted values with the actual values. If you plot the values into a table like the example, you can start getting some insights into how well the model performed. In a confusion matrix, you can get a high-level comparison of how the predicted classes matched up against the actual classes. If the actual label or class is cat, which is identified as P for positive, and the predicted label or class is also cat, then you have a true positive. This is a good outcome for your model. Similarly, if you have an actual label of not cat, which is identified as N for negative, and the predicted label or class is also not cat, then you have a true negative. This is also a good outcome for your model. In both these cases, your model predicted the correct outcome when it used the testing data. There are two other possible outcomes, and both aren't considered good outcomes. The first one is when the actual class is negative, so you got not cat, but the predicted class is positive, or cat. This is called a false positive because the prediction is positive but incorrect. Finally, there are false negatives. These happen when the actual class is positive, so you got cat, but the predicted class is negative, or not cat. That's it for part 1 of this section. We'll see you again for part 2, where we'll review calculating classification metrics. Hi, welcome back. We'll continue exploring how to evaluate your model. The diagram shows the confusion matrix of how two different models performed on the same data. Can you tell which one's better? Which is better isn't a good question to ask. What do you mean by better? Does better mean making sure you find all the cats, even if it means you'll get many false positives? Or does better mean making sure the model is the most accurate? It's difficult to see just by looking at the two charts. What if you're trying several models, using multiple folds, and have hundreds of data points to compare? To do that, you'll need to calculate more metrics. The first metric is sensitivity. This is sometimes referred to as recall, hit rate, or true positive rate. Sensitivity is the percentage of positive identifications. In the cat example, it represents what percentage of cats were correctly identified. To calculate sensitivity, take the number of true positives, or the number of positive identifications of cats, and divide that by the total number of actual cats. In this example, 60% of cats that were cats were correctly identified as cats. Specificity is sometimes referred to as selectivity or true negative rate. Specificity is the percentage of negatives correctly identified. In the cat example, this is the number of images that were not cats that were correctly identified as not cats. To calculate specificity, take the number of true negatives and divide that by the total number of actual negatives. So for the example, that's the number of not cats that were correctly identified divided by the total number of actual not cats. This means that in the example, 64% of not cats were identified as not cats. Now that you have these metrics for each model, knowing what your business goal is makes it easier to decide which model to use. Which model would you choose if you wanted to make sure you'll identify as many cats as possible? Model B would be a good answer if you're not concerned about having many false positives, that is. If you're not concerned about having incorrectly identified not cats. Which model would you choose if you wanted to make sure you identified animals that were not cats? Model A might work for this scenario. Again, it would depend on how many false negatives you can tolerate. If this was a classification of patients who had heart disease or not, which model would be best? This is where it gets interesting. A fun website might get a bad reputation if it can't identify cats correctly. But if you're trying to diagnose patients, your focus will probably be very different. It's important to understand the trade-offs you're making when you decide which model to use. There are also other metrics that can help you make your decisions. That's it for part 2 of this section. We'll see you again for part 3, where we'll start looking at thresholds. Hi, welcome back. We'll continue exploring how to evaluate your model. Classification models are going to return a probability for the target. This is a value of the input belonging to the target class, and it will be between 0 and 1. To convert the value to a class, you need to determine the threshold to use. You might think it's 50%, but you could change it to be lower or higher to improve your results. As you've seen with sensitivity and specificity, there's a trade-off between correctly and incorrectly identifying classes. Changing the threshold can impact that outcome. We're going to take a look at how you can visualize this. A receiver operating characteristic graph is also known as an ROC graph. It summarizes all the confusion matrices that each threshold produced. To build one, you calculate and plot the sensitivity, or true positive rate, against the false positive rate on a graph for each threshold value. You can calculate the false positive rate by subtracting the specificity from 1. After you plot those points, you can draw a line between them. The dotted black line from 0, 0 to 1, 1 means that the sensitivity, or true positive rate, is equal to the false positive rate. The point at 1, 1 means that you've correctly identified all the cats, but you've also incorrectly identified all the not cats. This is bad. Any point on this line means that the proportion of correctly classified samples is the same as the proportion of incorrectly classified samples. The point at 0, 0 represents that there are 0 true positives and 0 false positives. A model that has high sensitivity and low false positive rate is usually the goal. So it's considered to be better when the line between the threshold recordings is closer towards the top left corner. If you had the data from 2 models, you could plot out the ROC curve for each model and compare them. However, that can be tedious. There's another graph you can use for this, which we'll look at next. Another evaluation metric you can use is the area under the curve receiver operator curve, which is also known as an AUC-ROC. The AUC part is the area under the plotted line. When the AUC is higher, it means the model will be better at predicting cats as cats and not cats as not cats. You can use the AUC to quickly compare models with each other. With the 4 numbers from our confusion matrix, you can calculate the model's accuracy. This is also known as its score. You can do this by adding up the correct predictions and then dividing that number by the total number of predictions. Though accuracy is a widely used metric for classification problems, it has limitations. This metric isn't as effective when there are a lot of true negative cases in your data set. Think about the cat, not cat example. If most of your accuracy is based on true negatives, it says that your model is predicting what isn't a cat. In this case, you might not feel confident in your model's ability to predict cats after you roll it out into production. This leads to an example of why it's important to make sure that the metric you choose for model evaluation aligns to your business goal. Think about the credit card fraud example. In using accuracy as your main metric probably isn't a good idea because you have a lot of true negatives. Your high true negative number might hide the fact that your model's ability to identify cases of fraud, that is, to identify true positives, isn't ideal. As a credit card company, it's probably unacceptable to have less than almost perfect performance identifying fraud cases. That would drive customers away, which would be the opposite of what you'd want to achieve from a business standpoint. This is why 2 other metrics are often used in these situations. The first one is precision, which essentially removes the negative predictions. Precision is the proportion of positive predictions that are actually correct. You can calculate it by taking the true positive and dividing it by true positive plus false positive. When the cost of false positives is high in your particular business situation, precision might be a good metric. Think about a classification model that identifies email messages as spam or not. In this case, You don't want your model to label an email message as spam and thus prevent your users from seeing that message when it's actually legitimate. Or consider an example of a model that needs to predict whether a patient has a terminal illness. In this case, using precision as your evaluation metric doesn't account for false negatives in your model. Here, for the model to be successful, it's crucial that it doesn't falsely predict the absence of illness in a patient who actually has that illness. Sensitivity would be a better metric to use for this situation. But it doesn't always need to be one or the other. The F1 score combines precision and sensitivity together. It gives you one number that quantifies the overall performance of a particular ML algorithm. You should consider using an F1 score when you have a class imbalance, but want to preserve the equality between precision and sensitivity. But what do you do if you're dealing with a regression problem? In that case, there are other common metrics you can use to evaluate your model, including the mean squared error. The mean squared error is frequently used. Its general purpose is the same as what you saw with classification metrics. You determine the prediction from the model, and you compare the difference between the prediction and the actual outcome. More specifically, you take the difference between the prediction and actual value, square that difference, and then sum up all the squared differences for all the observations. In Scikit-learn,